Yeah, so hello, thank you for the introduction. And so this talk will be about security models for long-term integrity solutions. And it focuses on really getting a security proof for some solutions which were presented earlier, because it seems that no security models exist yet. So the motivation is similar to what we were hearing before. In our scenario, we are thinking of a more and more digitalized world. And in this world, we have electronic health records, and we have text data, which is stored electronically, and we have all kinds of other documents which are stored on the computer in digital form. And if we want to protect this data over a long period of time, then we need something like a digital archive. And this is what we are concerned with. For such a digital archive, we have two main important protection goals. And one is integrity, so that means preventing unauthorized modification of the archive data. And another one is confidentiality, and that means preventing unauthorized access to the data. In this talk, we will mainly focus on integrity. So we also heard what in this context integrity means, but I will briefly repeat it. So we think of this of integrity in this context as the following. We have a document which was archived at a time t0, and later it is retrieved at time t. And integrity means that the document has not been changed since the time of archival. In the classical case, we use electronic signatures for guaranteeing integrity. However, as I want to motivate now, complexity-based cryptography, which typically a digital signature scheme is, does not provide long-term protection by default. So for example, we have seen these slides in a previous talk yesterday, but I want to briefly repeat it. We have the paper or the signature scheme based on RSA, which was proposed originally in the paper 1978 by Rivers, Shamir, and Edelman. And they propose for future development, or to be secure against future development, we should use a security parameter which has 200 digits. And then if we look at the underlying hardness assumption for how long does this security suggestion actually last, and in 2009 we can see 200 digits is not secure anymore, so RSA based on 200 digits security was broken by then. So this was approximately 30 years of security. So if you have really long-lived data in an archiving system, 30 years might not be enough. And another example is Shor's algorithm. And this tells us basically that if we have quantum computers, then we have no security based on RSA anymore, because it's just broken no matter what the security parameter is. So the typical scheme, or the typical schematic that we have is, when we use complexity-based digital signatures, we can expect some lifetime, which is colored, which is depicted by this colored graph. But after this lifetime, the protection is lost. So it does not really provide long-term protection by default. We have to get some measures against losing the protection at some point in time. The good news is that long-term protection is possible, as we've seen before. And I will also briefly explain how it works for the integrity case, which is based on the simple mechanism, or the basic mechanism of timestamping. This is, for example, specified in the RFC 3161. So the idea is we have a document owner with a document and a timestamping authority. The document owner wants to get a proof of existence or a proof of integrity from the timestamp authority. And what he does, he hashes the document, sends the hash value to the timestamp authority. The timestamp authority signs the hash with the current time, so it is trusted to always put the correct time in the timestamps. Then the timestamp is generated. It's basically a signature on this data, and it is sent back to the user. So that is the fundamental way to create a proof of existence for this document, a proof of integrity with respect to the time of archival T. However, this is based on signatures, on digital signatures, so we have to find a way to prolong the security again. So this is described in RFC 4998, for example. And to achieve long-term integrity protection, it was also described by Denise before, we basically do a sequence of timestamps. So we have an initial timestamp on the document T0, which was just explained. And it has a certain period of time for which it remains valid. For example, the validity of the digital signature of the public key certificate. And before that validity period is over, we have to prolong it. And it is specified that you prolong it by getting a new timestamp which is currently valid on the document and the previous timestamp. And by this you prolong because you prove that you knew the document and the timestamp at the time when it was still valid. And you can do this several times, obtaining a timestamp chain or a timestamp sequence. So the integrity proof for the document is basically this sequence of timestamps. And when somebody, a verifier, gets the document and the sequence of timestamp he has to check, is the last timestamp valid when at the time of verification of the integrity? Is for all timestamps, are they issued when the previous timestamp was still valid? And we have to check that the timestamp refers to all the previous timestamp and the document, and especially the first timestamp must refer to the document itself. So what we want to mainly address in this talk and in the paper that comes with this talk is what is the security of this construction? It seems intuitively right to do this, but also there have been proposed other solutions. For example, it was proposed to do it without the document, and then people saw, okay, we might have problems with doing it this way when the hash function becomes insecure, which is usually used in this process. So we really want to have a security proof for such a construction and estimate the security in the context of real-world systems. And there's related work, which one of the authors also sitting in the room, and this is going in the same direction. It's looking at long-term security from a different perspective. But so it's work of Canetti, Join, Kainer, Lynch, Pereira. And the title of the work is Modeling Computational Security in Long-Lived Systems. So it's more the broad perspective on this kind of topic. So their motivation is as follows. And I hope I presented correctly. If I'm not correct, then please tell me. But my understanding is as follows. The motivation is, so traditionally in security models, we have a polynomial time adversary. This means the adversary is allowed to do, there's a fixed security parameter, and the adversary is allowed to do a polynomial number of steps in this security parameter. However, then the question is, if we have a system which is really running for a long time, maybe a super polynomial time, then, so what does it mean then, if the adversary is not allowed to run as long as the system is running? So, and if we allow really the adversary to run for exponential time, then security, achieving security is actually kind of difficult, and so usually you want a polynomial bounded attacker because otherwise you cannot prove security. So what the idea is, in this framework that they propose, they distinguish between the machine time, so the number of steps that the computer, that the adversary computes, and they also have a notion of real time. And then they can say, okay, we do not bound the overall power of the attacker for the whole time, so he may actually run for unlimited real time, but the computation power per unit of real time is bounded. And this allows them to define and model some of the following notions. So they have a framework, they give a framework for compositional security in long-lived systems. And in such kind of a framework, as was explained by Professor Müller-Quade before, what you do for proving security is the following. So you have a component, and you want to prove the security of this, and you formulate, so in a very simplified way of putting it, you formulate the ideal functionality of that component, and then you show whatever you do with this component, if you interact with the real component, it looks the same to you as if you interact with the ideal component. So you cannot really realize if you're using the ideal thing or the real thing. And this, by definition, is security, of course, if you always get the perfect result. And what they do in this paper is they have a notion of long-term indistinguishability, meaning that the adversary or the environment that uses these components is running for a very long time, but is polynomial bounded per unit of real time. And on top of that, if you have multiple components for which you can prove this indistinguishability notion, then you can also compose, according to some theorems given, these components and still maintaining the indistinguishability relation. So especially they have sequential composition, meaning that components that run after one another can compose without problems while maintaining the indistinguishability notion, and also a certain number of parallel components can be composed maintaining the indistinguishability. So they also apply their framework to a long-term integrity scheme, and the result is as follows. So they show if you compose the long-term integrity scheme with real timestamping services as they are implemented in the real world with possible security failures, then this is indistinguishable from composing the same integrity system with ideal timestamping services. So, however, what I find is not solved in this paper is that they don't have a security notion for the ideal for the whole thing. So there's a security result for the composition, but there's no security notion what the original scheme, as you see, they use the same integrity scheme in the ideal world and the real world. So there's no security notion for the long-term integrity scheme itself. And also, what does not seem completely well is that adversaries still have a computational power which is fixed per unit of real time. So they do not model something where the adversary is getting faster over time. So what they notice, and I think this is quite interesting, is the probability that an adversary may break a secure system over a long period of time can only increase. So you cannot really reset the adversary and say, okay, well, yeah, you have to start from the beginning. But basically, over time, the probability that you break, for example, a single timestamp by this breaking the overall integrity protection is only increasing. And so for us, a really important question is for how long can we protect integrity of a system? And this is also something which is left open in this paper. And we think that it requires really a quantitative security statement. It's not something where you say, okay, it is secure or not, but maybe it's secure until this point in time, and beyond that there are no sufficient security guarantees anymore, depending on what the context of the long-term integrity scheme is. So now that brings us to our work, in which we focus really on the security of long-term integrity protection in particular. And the challenges are as follows. I briefly summarize what I did say before. So we want to develop a comprehensive security model, especially for these kind of integrity schemes. And also we want to be able to use this model to estimate over which time period an integrity scheme can be used securely, or also just saying, depending on the timestamp services that you use, what is the security level of this scheme in the long term. So we start basically by formally defining what an integrity scheme is. And we think of it as it has three algorithms. The first algorithm is protect. It protects the initial document or the data object D and outputs an integrity proof in the reference time T0. Then there's an algorithm prolong, and it gets as input the same document as before. It gets the current integrity proof, and it generates a new integrity proof which is valid for a longer period of time than the current proof. And finally, we have the algorithm verify, and it gets the document, the reference time, and the integrity proof. That is the current valid integrity proof, and outputs a bit either showing that the integrity proof is valid or if it's not. And for all of these algorithms, we allow them to use other cryptographic services. For example, they may query timestamping services to get timestamps because, as we saw in our construction, basically the proof consists of a sequence of timestamps. And now we cast the construction that was described before into this scheme definition. So the protect algorithm is basically generating an integrity proof, which is a timestamp on the hash of the document at time t0. The prolong algorithm is all the previous timestamps, which are contained in the integrity proof in the current one, plus a timestamp on the document and all the previous timestamps. And last but not least, we have the verification algorithm, which checks that every timestamp refers to all the previous timestamps in the document, which is the first condition. And the second condition is that the schemes are valid when they were used. Okay. So what is the adversary model that we have to consider in this against such a scheme, in the context of such a scheme? So first of all, we want to think of the computational model. And here I think it's important in the long term that we do not just allow adversaries to be modeled as Turing machines, for example, which may only evaluate efficiently Boolean circuits, but we also may have to face an adversary which uses a quantum computer, and then he may actually use do efficient computations in quantum circuits. So for this, we use a more general computational model, which was explained, for example, by David Deutsch in his paper on quantum Turing machines, and it captures Turing machines as well as quantum Turing machines. And we think the computational model should be based on something that is this general, which captures a wide variety of other computational models. Then we also want a notion of real-time in our model, because, for example, we want to be able to say what it means a timestamp authority uses the real time to put it into timestamps. And we also want to express, similar as the framework described before, we want to be able to express computational constraints on the adversary with respect to real time. And modeling real time is actually not straightforward in a formal sense. And we use an approach which is similar to some approach which was proposed by Jörg Schwenk in 2014 for modeling security of key authentication. Authentication. So he uses a global clock, and the clock is incremented whenever the adversary makes a query to its environment. And our model of time is similar to that. We also have a global clock. However, we allow the adversary to decide when he wants to advance through time, which models that the time is not actually dependent on the number of queries, but we still have a notion of time and can bound the adversary with respect to the notion of time. But the adversary may actually has a little bit more influence, so it's a little bit more general than incrementing time whenever the adversary makes a query. So having this in place, we can restrict the adversary power to time with respect to time. So, for example, we may say, okay, at one point in time, he has a computer which is computing at 1 megahertz of operations per second, depicted here, and then later at a certain point, he may use a much faster computer. We can also express using this formalism that the adversary may only get use algorithms that are available at certain points of time. So if we really are convinced that a certain algorithm has only been developed maybe at the year 2010, or for example the Shor's algorithm in 1997, we could say in this model, okay, before that time we think that no algorithm was available that these computations could be done efficiently, and we can express this in the model. And we can also say, similarly, we can say, okay, certain computational architectures become available at certain points in time. And by this, we can bound the computational power with respect to certain events that may happen or that have happened in the past. So also the adversary may use cryptographic services, of course, so he may query timestamp services. He may also use random oracles, which we use to model hash functions. So this is a technical formality, but we use it in our model, and it's commonly done in security models to replace the usage of hash functions by usage of random oracles. And in particular, an adversary may also compromise in our model services that he uses. So he may generate timestamp with the wrong time if this timestamp service is not valid anymore. So the timestamp service has a certain validity period, and after that is over, we allow the adversary to generate wrong timestamps. And for hash functions, we allow the adversary to program the hash function. That means that he can choose for values for input hash for pre-images. He can choose hash values afterwards when the security of the hash function is not given anymore. But he cannot change values or hash values for which he already queried a pre-image. But he may use for new queries, he may choose the hash result. So now we have to think of having so we have the definition of the scheme in place, and we also have the adversary model. So what can the adversary do in this context? Now we really have to think of what is the security notion for such a long-term integrity scheme. And we think a good security notion is that the long-term integrity scheme, which by default, at least in the current specifications, always uses a set of cryptographic services, and we think it should be as secure as the cryptographic services that it uses for generating integrity proofs. So we can formalize this notion in the following game. So the adversary in this game may use, as I said, he may use and compromise also cryptographic services. And at some point he has to output a document, a time, and an integrity proof, and he wins the game if if this proof is valid for the document and the time, and no timestamp was actually issued for this time. So he presents a valid proof, but he didn't really get a timestamp for the document. So there's no evidence that he really did know, or that the integrity was intact at this point in time. And the technical point that I want to mention is, so in the protocols that are specified, timestamps are issued on hash values. So we cannot really say a timestamp was issued for D, but we must say a timestamp was issued for the hash value. And because we use random oracles, we can say a random oracle query for D was done before time t0. So this is what is actually formally done in the model. So now we can formulate the security definition, and it looks as follows. A long-term integrity scheme, LTIS, is secure if for any adversary interacting with a set of services S, for every service I and S, there exists an adversary BI with computational resources comparable to that of A until the end of validity of service I. So there must be, for every service, there must be an adversary that uses the original adversary, and the adversary BI only has computational resources as long as the cryptographic service is valid. And then the probability that the long-term adversary A breaks the long-term scheme must be smaller than the probability that one of the BIs breaks the service I within the validity period of the service. And the sum over these probabilities, I mean. So this is really the notion that we want to achieve. The overall scheme must be as secure kind of as the sum of all the single schemes. And for technical reasons, we have a constant in here, which comes from the reason for this is using the random oracle model. Unfortunately, we could not do it without the random oracle model, so we have a small constant in here. And the results using the security notion, we can prove the security of the construction that are described. And it's basically a reduction to the security of the signature schemes that are used by the timestamp services and some properties of the random oracle. So we can reduce the security, giving a formal reduction. We can reduce the security of the long-term scheme to the security of the single services. So what we get is exactly this, as in our definition, where the C, the constant, is the number of hash values that we allow to be used in an integrity proof. So there's a certain, we can basically count the number of hash values in an integrity proof, and if we bound this number, then C is this number. So this now allows us to estimate in which context we get which level of security. So in the first place, we want to look at security level of the timestamping services of 80 bits. And if we consider that there are 10,000 services active over maybe a period of 100 years, and we allow up to 2 to the 16 number of hashes in an integrity proof, then we get a resulting security level of 47 bits. And this, of course, if you use stronger security for the services, you get a stronger security in the end. But this is the relation in such a context. And the similar thing we can do, of course, the same accounts for if we change the constant, the number of hash values that we allow. If we only use 100 hash values, in the reduction tells us, okay, then we get this security property, assuming that we have a security level of the service of 18 bits. So there's, again, depending on the number of the parameters that we use for the scheme, there's a certain reduction in security according to our reduction algorithm or our reduction proof. And this brings us to the conclusions. So we have given a new way to formulate security in long-lived systems, which is based on previous work, but incorporates a few other and novel techniques. And we have given a security proof, the first security proof to our knowledge, which really captures the security of long-term schemes, long-term integrity schemes. And it allows us to get a more concrete understanding of the security of such schemes. As future work, it would be really nice, we think, if we could do a similar security proof without random oracle model. And we would also like maybe to do the same thing for the long-term binding commitments, which were just described by Denise. And with that, I want to conclude my talk. And if there are any questions, I try to answer.